our usual 2 pieces of advice, because they're good pieces of advice. Do problems. The more problems you do, the more natural things become. And also, take care of your health. We had a good walk. That's good. But, make sure you get enough sleep. Make sure you eat some good food. And scream in your pillows as you need. Hydrate. Don't overhydrate. There's only so many restrooms near the test. But take care of your health. And for this exam, we'll add a third thing, which is know your table. Don't try to be like, I'm just going to memorize it and I'll never look at my table. Know your table. In other words, we have our handy-dandy equation sheet. So have it handy. And pro tip, this is detachable. So if you just take your exam and you just rip off the last page, you don't have to reattach it. And you can keep it after the exam as a souvenir of all the good times. And so the more comfortable you are with your table, the faster the exam will be. All right, so here we go. 9 problems, and we'll try to go at a bit of a pace. So number 1, find the following. So this is us practicing our Laplace transforms. So we have 3 problems, 3 subproblems. So 3 for the price of 1. Okay, so for part A, well, this is like a very long expression. But remember, Laplace transforms break up over addition, and you can pull constants in and out. That's another way of saying Laplace transforms are linear. So if you see lots of things being added or subtracted, just go ahead and say, let's pull it apart. Okay, so what do we have? Well, we can say this is 7 Laplace of 1 plus 4 Laplace of e to the 3t cosine 2t plus our Laplace. Now here, the square root of t e to the t, we can rewrite this. And we're going to think of them as sort of separate pieces. So square root of t, that's t to the half. E to the t, well, that's e t to the over 2. Essentially, think of it as the square root of e to the t is e to the t to the half. So it becomes e to the t over 2. So you want to write things in essentially table-friendly ways. Because your pretty much only chance for taking a Laplace transform is it's on the table. So if it's not on the table yet, you got to make it look like what's on the table. All right, so let's see. What can we do? 1, no problem. It's on the table. Good. E to the 3t cosine 2t. Now, the table is not the largest table possible. You can make much, much larger tables. So the goal is to say we have collections of rules and we use them in sort of unison. So there's 2 rules in particular. So the e to the 3t cosine 2t combines the cosine rule with the multiplying by an exponential rule. So what does this tell us? Well, it says you take the cosine, and then what you do is everywhere where you see s, you're going to do a shift. So the exponential function, when you're taking a Laplace transform, and there's an exponential involved, that's going to correspond to a shift. So in particular, this e to the 3t tells us that s is going to become s minus 3. And, okay, well, we should make some notes. We should note here Laplace transform of 1. That's 1 over s. And, okay, cosine 2t, just by itself, that would be s over s squared plus 4. All right, now our last term, and again, we see an exponential, so we say, okay, so here, this is e to the 1/2 times t, so that says s is going to go to s minus 1/2. That's the shift, our rule here. Now, t to the 1/2. Well, that's t to a number. There's sort of two cases. There's t to a whole number and t to just some number. So this is t to something, not a whole number. So according to this rule, this would be gamma of, well, 1/2 plus 1, 3/2 over s to 1/2 plus 1, 3/2. Yes? I'm just putting notes right now. Okay, so what happens? Well, we have the first piece is going to be 7 times 1 over s. No big surprises. Then the plus 4. Then the next piece, well, I start with the s over s squared plus 4, which is really s squared plus 2 squared. But everywhere there's an s becomes s minus 3. So s minus 3 upstairs, s minus 3 squared plus 4 downstairs. And we don't have to simplify. We'll leave it like that. And then, well, our last piece, we have this s to the 3/2. That's going to become s minus 1/2 to the 3/2. That leaves us with one thing to talk about. And the last thing to talk about is this gamma 3/2. Now, they may say, you can leave it as gamma, and they may say, no, simplify if you can. Well, can we? Looking at our table, there are some rules about gamma. And so, in particular, if you ever see gamma of something with a half, 3/2, 5/2, 19/2, then you can combine these rules to figure out what's going on. So, well, what is it? Gamma of 3/2 is 1/2 plus 1, because, well, 1/2 plus 1 is 3/2. So according to the rule, if you use beta equals 1/2, this is 1/2 gamma 1/2. You say, well, okay, well, what's gamma of 1/2? Now, you might have to use the rule again, but in this case, you say, oh, wait, it tells us. That's equal to square root pi. So if you ever see sort of a t2 with a 2 in the denominator, like t to the 1/2 or t to the 3/2, whatever, that means there's a root pi hiding. And so, what do we have? Well, we're going to put in the gamma 3/2, which is 1/2 root pi. And there we go. That's the answer for part A. So break it up. Use the rules. And you'll be okay. All right. Well, let's go straight on and start part B. Okay, so here we are, part B. And we're finding the Laplace of t minus 2 cosine t squared. Okay, well, is there a rule for when we square a function on our table? No. So what do? Well, we do algebra, right? So a lot of the work for doing Laplace transforms and inverse Laplace transforms is rewriting and just saying, okay, how can I rewrite this, make it table friendly? So if I see a square, say, well, that's the same as the Laplace of t squared, and then we have the cross terms, so that'd be minus 2 times t times 2, so altogether it's minus 4t cosine t, so 2ab, like a squared minus 2ab, so that's our minus 2ab plus b squared. All right, t squared, we can handle that. That's on our table, t to a whole number. T cosine t, can we handle that? Yeah, it's actually right on our table. Wow, cool. Cosine squared t, can we handle that? Well, cosine, yes. Cosine squared, no. But our formula sheet has lots of cool stuff. Like cosine squared, we can rewrite that using power reduction. So cosine squared, no, but through the miracle that is trigonometry, what a glorious miracle it is. We can say cosine squared, we'll just put a note underneath here. This is 1/2, 1 plus cosine double the angle, cosine 2t. So 4 times 1/2 makes a 2. So we have a plus 2 cosine 2t. All right. Now, can we do each piece? Well, yes. And we don't even have to do anything very tricky. All the pieces we can handle term by term. So, take your time. T squared, n equals 2. So we should have a 2 factorial, which is 2, divided by s to the 2 plus 1, s cubed. Minus 4, t cosine t. So we come down, t cosine bt, so that's b equals 1. So this is going to be s squared minus 1 squared on the top over s squared plus 1 squared down below. All right, good. 2, well 2 is 2 times 1. So you can pull out the 2 and then 1. We know how to handle that. That's 1 over s. And now we have finally another 2. That can come out and cosine 2t. All right, well that's b equals 2. So that would be s over s squared plus 2 squared. So s squared plus 4. And we're done. So that's our answer. All right. Any questions for A and B? Good. Well, that leaves us with C. All right, well, let's see if we can make it work. We've got a little bit of space left. So part C. So we're asked to find the Laplace of t times integral 0 to t of tau, g of tau, d tau, where, well, we don't know what g of t is, but we know what the Laplace of g of t is. Laplace of g of t is s squared plus 1 to the minus 1/2. So, oh, wow, what a function. There is actually a well-studied function that has this property. Unfortunately, not well-studied for our class, and that's well down the road. So we're not going to find g of t. That's not our goal. So what do we do? Well, this is what I would call a classic onion problem. Layers. Layers upon layers upon layers. And the trick is, can you peel your onion? Can you get through it? Hopefully with no tears. So, let's talk about the rules we need to focus on. We have t's multiplying, and we say, okay, well, we know something about t multiplying because there's a rule. Now, in particular, this is sort of the generic rule for any t to the n, but we can extract from that. We'll make a little note here that t equals 1. So if we just have a single t, well, that tells us that we're going to take minus the derivative of f of s. So that's going to be involved at some point. Well, what else? Well, another thing we see is that there is an integral. Now you have to be careful. Integrals show up in our tables in 2 ways. So make sure you know how it's showing up. Now you might say, well, how does it show up in 2 ways? Well, it shows up here and right above it. Both of them involve an integral. So you want to make sure you know the difference. Well, what's the key difference between these? This part needs a t minus tau. That's our convolution. Do we have a t minus tau here? No. So we're not doing convolution. So make sure you know what you're doing. Also make sure you know what you're not doing. So we're not doing convolution. So that says, okay, what do we have? Well, it says, and we'll put it down here for our reference, integral 0 to t of whatever function you're working on, you add a 1 over s. So it's 1 over s f of s. And those are the two things we need. Okay, so how do we start this? Well, we understand how to do g of tau. So that's our innermost layer. That's given to us. So now let's add a layer. So if we can do g of t, can we do t times g of t? Answer is yes. So the Laplace of t, g of t, says we're going to take minus the derivative of what function? Of this s squared plus 1 to the minus a half. Yes? Because it says t says there's a minus a derivative, and then it's a derivative of what? Well, take the Laplace of what you're attaching it to. In our case, we're attaching it to g, so what's the Laplace of g? It's s squared plus 1 to the minus a half. All right, well, what's that derivative turn out to be? Well, minus a half comes down. Chain rule, s squared plus 1 to what power? Negative 3/2. Good. Anything else? Times 2s. Well, two minuses make a plus. Just as we know, two wrongs make a right. The half and the 2 cancel. So we have s times s squared plus 1 to the minus 3/2. Okay, that's the innermost layer. And, well, I should say one thing past the innermost layer. Okay. Now, are we ready for our next layer? Our next layer. Let's do this integral. So, what can we say about the Laplace transform of the integral 0 to t of tau, g of tau d tau? What's the rule tell us to do? There's a 1 over s, and then you multiply that by the Laplace transform of what's on the inside of your integral. In our case, the inside is this function, tau g of tau, or really t g of t. So we're going to take this 1 over s and multiply it by what we just found. So times s squared plus 1 to the minus 3/2. Well, does anything simplify? Yeah, the s's cancel. So this becomes s squared plus 1 to the minus 3/2. All right, is that our answer? No, because our onion continues. Oh, tears of joy. Just, it feels too soon to stop. So what's our next layer tell us to do? So we have now a t in front. So if I add a t in the front, what does it say we should be doing? Well, if I have a t in front, it says take minus the derivative of everything else. So we want minus the derivative of this part, the integral from 0 to t, tau g of tau d tau, which we found. It's s squared plus 1 to the minus 3/2. Okay, so we do this derivative. Well, that's going to become, we have the minus sign. Minus 3/2 comes down. S squared plus 1 to what power? Minus 5/2. Anything else? Times 2s. Can we simplify anything? Two negatives. There's two 2's. So we're left with 3s times s squared plus 1 to the minus 5/2. And now what do? We box it. Oh, good. It's nice to know when you've reached the end of a problem. So this problem, it's two ideas, but it's just a matter of we apply them. And we have to know which order to apply them and when they apply. And I like to go from the inside out, just adding one more layer, until we have our answer. Good times, good times. All right. Are we good? Yes. You look great. So, well, that was a good practice for Laplace, but we also need to do inverse Laplace. Now, keep in mind that when we write our formulas, we only write the Laplace version, but each formula always comes in pairs. So there's always sort of an inverse Laplace formula lurking in the background. All right, so let's begin. Another 3 set. Oh, wow, good. Well, we have 11s squared minus s minus 6 divided by s times s plus 1 times s minus 2. How are we going to make progress on this problem? What do we need to use? Yes, partial fractions. At some point in the exam, you should anticipate partial fractions, because this is sort of the de facto algebra problem that shows up when it comes to Laplace transforms. So at some point, not all the time, but be ready. So know how partial fractions work. And in particular, remember, partial fractions, you have to have polynomial over polynomial. If you don't have polynomial over polynomial, then you need to do something to make it look like that. Well, we do have polynomial over polynomial. So most of the work for this problem is not going to be the inverse Laplace. It's going to be getting it ready for inverse Laplace. In other words, rewriting it, preparing it. So, all right, let's get to work. So we have 11s squared minus s minus 6. Divide that by s times s plus 1 times s minus 2. We're not going to have anything too crazy. The denominator will be either really super trivial to factor or it will already be factored. So don't panic about, oh my gosh, am I going to be able to factor the denominator? The important thing is make sure you know the form. So, what do we do? What's the goal? The goal of partial fractions is to pull things apart. And in particular, we're going to pull things apart so that we have something over the first term, something over the second term, something over the third term. Now, make sure you know the rules. There's a couple rules. What's going to be upstairs? Like, for example, what do we want to put over the s? A. How about s plus 1? B. S minus 2? C. All right, good. Now, we'll do something which involves a square in a second. But what if I had said it was s times, I don't know, s plus 1 times s plus 1. So s plus 1 was a repeated root. What would you do there? So be careful. If you have repeated terms, you have to work your way up. So if it's the s minus 2 that's repeated, you'd have s minus 2 squared, and then upstairs you'd only have constants. All right, but let's do this one. Okay, so once you have the form, everything else works pretty quickly. Clear out your denominators, and by that we mean multiply both sides so that what's left has no fractions. We've struggled with fractions in the past, so we're like, okay, we're not going to go that way again. So we say, okay, so 11s squared minus s minus 6 is equal to a, s plus 1 times s minus 2, plus b, s times s minus 2, plus c, s times s plus 1. Now, there's multiple ways to do partial fractions. We're not playing the game like you have to think of our way to do it. We understand that you've learned different ways. So use the one you're comfortable with. I like to use the one where I'm less likely to make a mistake. So that's why I choose what I do. If it doesn't work for you, that's great. Find something that works for you. I like make good choices. It just feels right. So how does make good choices work? Make good choices work by saying, hey, this is true for any value of s. So pick nice values of s that makes lots of zeros. So what's a good choice? 0 is a good choice. Plug in s equals 0. 0, 0, minus 6. A times 1 times minus 2, that's minus 2a. 0b, 0c. So a equals 3. Another good choice? Negative 1. All right, negative 1 squared is 11. Minus minus 1 is a plus 1, and minus 6. We're going to get a times 0. That goes away. Then we're going to get b minus 1 times minus 3. And then c times 0. Well, 11 plus 1 is 12, minus 6 is 6. Minus 1 times minus 3 is 3. So this is the same as saying 6 equals 3b. b equals 2. Any more good choices? 2. And by the way, if you run out of good choices, just pick some reasonable numbers. Or if you like, expand and compare coefficients. Oh, ooh, big number. 11 times 4 is 44. Subtract 2, subtract 6. That's going to be an interesting thing. A times 0. B times 0. So we get C times 2 times 3. All right. Well, 44 minus 8, that's a number. That's true. It is a number. It's 36. So 36 equals 6 times C. So that tells us C equals 6. All right. So all of this work is to say the following. We can now pull apart this polynomial over polynomial into smaller polynomials. But not just smaller polynomials that are friendly to the inverse Laplace. Here's a mistake I've seen several times. Students are very good at finding these numbers, and they do an excellent job, just like you'll do an excellent job. But then they forget to put them all in. So don't forget to put them all in. This especially happens when you have like a square term downstairs, s squared plus 1. The number of students who forgot was very sad. So 3 over s, 2 over s plus 1, and 6 over s minus 2. And now, each one of these individually is pretty straightforward because they all fall into this camp. They all are part of the exponential functions. So you just have to see it's s minus something. So, well, in this case, the 1 over s minus 0, c to the 0, but it's the same as 1. So we end up with 3. S plus 1 is the same as s minus minus 1. So this next term will be 2 e to the minus t. And then the last term, 6. So I'm using the fact that we're linear, so we can pull out the 6. And also linear says do each one individually. S minus 2 e to the 2t. And there's part A. Notice how most of the work is partial fractions. And the actual inverse Laplace, that's not too bad. The table part's not bad. Okay, part B. S plus e to the s quantity squared over s times 9s squared plus 1 e to the 2s. Well, what should we do? Yeah. Can we do partial fractions? No, because it's not polynomial or polynomial. So you got to be careful. All right, so we're going to work on rewriting it. Okay, so what do we have? Well, let's expand the numerator as has been suggested. S plus e to the s squared over s 9s squared plus 1 e to the 2s. So upstairs, we're going to get s squared plus 2s e to the s plus e to the 2s. Downstairs, we'll have s 9s squared plus 1 e to the 2s. All right. Now what should we do? And not partial fractions, not yet. Well, yeah, so essentially, we're going to take advantage of these plus signs. So plus upstairs in the numerator, those are the good pluses. Those are saying we can pull them and handle them each term by term, one at a time. All right, so we're going to have the following. We're going to have three pieces, s squared over s 9s squared plus 1 e to the 2s, then plus 2s e to the s over s 9s squared plus 1 e to the 2s, and then e to the 2s over s 9s squared plus 1 e to the 2s. Okay, so we've used the fact we have addition in the numerator to pull it apart. Well, can we do anything to simplify? And spoiler alert, the answer is yes. How about in the first term, term by term? What are some things we can do? We can cancel a single s. That's good. And this e to the 2s, we can move that upstairs. So an e to the 2s downstairs becomes what upstairs? E to the negative 2s. Now one other thing, what about this 9? Are we okay with the 9 there? Or do we want to do something with it? Pull it out. Now why do I say that? Well, the thing I'm looking at is I'm looking at my table and I say, well, it's feeling a lot like a sine or a cosine, but that doesn't have anything in front of the s squared other than a 1. So if I want to use the sine rule or the cosine rule, and we'll figure out which rule is the right rule, I need to make sure it really fits the mold. So I don't want a 9. So we pull it out. It's the right answer, as somebody has said. So, all right, so I'm going to pull a 9 out from the downstairs. So that's 1/9. And then we have s. Now there's an e to the minus 2s on the end. And what does the 9s squared plus 1 become? S squared plus 1/9. And by the way, 1/9 is 1/3 squared. All right. Middle term. What can we do? We can still cancel an s. What about this e to the s and the e to the 2s? Yeah, we can combine them, right? So if we move this upstairs, it'd be e to the minus 2s. Let's pull out the 9 again, so plus 2 over 9. And we'll have a 1 over s squared plus a 9th. And then we'll have e to the minus s. We'll come back and revisit this. This last one, anything simplify? E to the 2s's cancel. So, okay, that's great. So we're left with a 1 over s 9s squared plus 1. We'll work on that in a second. Okay, so let's check in. Whew. We might have to go to a second page to finish this particular problem. How are we doing on this term? Are we good? We're ready to go? All right, good. We're table ready. How about here? Are we good? Are we ready to go? We're almost ready. Thinking about the table, this looks most like the sign. What's missing? Yeah, we're missing the something upstairs, should be a B. So what are we going to do? We're going to put it. And I'm like, what? We can't just do that. Well, we can if we do what? Multiply by a 3. And yes, we can simplify things, and we'll do that in a few minutes. All right, this last part, what are we going to need? So now we're happy, by the way. And here, partial fractions. Good. Just when you thought you were done, partial fractions pulls you back in. Oh, what a glorious time to be alive, that we can continue doing partial. You probably didn't think you'd get to do partial fractions. After you finish calculus, you're like, oh, I'll never see a partial fraction ever again. And yet, here we are. Okay, so. All right. Oh, that pen's almost run out. Okay, so let's try a different pen. So 1 over s. And I know I need to clean up the 9s squared plus 1. I'll do that in a few minutes. So that's something over s, something over 9s squared plus 1. What's on top of the s? A. Oh yeah, A, you betcha. What's on top of the 9? What's on top of the 9s squared plus 1? I know, like BS. No. B times S, yes. Plus C. Yeah, so this is an irreducible quadratic, so make sure you have the right pieces. The procedure is still the same. Clear your denominators, make good choices. And sometimes when you have a 9s squared plus 1, good choices may be harder to come by, but we'll do the best we can. We'll make as many good choices as we can. All right. Oh, whoops, and we should do that on both sides. Okay, so we have that 1 is equal to A times 9s squared plus 1 plus B times S plus C times S. All right. Well, yeah. There's one good choice. Should we go ahead and make that choice now? What's the good choice that pops out? 0. So, okay, S equals 0. We make our good choice. We come to the conclusion that 1 equals A. Okay, that's good news. All right, well, what about the rest? Well, let's just, if we're stuck in one method, jump to another method. What's another method you can do for partial fractions? You can expand and group your coefficients. So, for instance, the constants. Well, the only constant is the A. How about something times S? Is there anything that's something S? C. All right. Is there something S squared? Yeah. 9A and B. So comparing our coefficients, well, this has to equal 1, which says that A equals 1. Oh, yeah, we know that. What's true about C? Equals 0. What's true about B? So we know A equals 1, so 9 plus B equals 0. So B must be negative 9. All right. Well, this is one of those times when it's just, we're going to have to do a weird move things around. So, okay. So, continuing, we have our first terms, which we were happy with. This is one of the things you have to be patient with these problems. Here we can cancel, a 3 goes into 9, so a 2/3 times 1/3 over s squared plus a 9th e to the minus s. And now this 1 over s times 9s squared plus 1, well, a equals 1, so that's plus 1 over s. B equals negative 9, and C equals 0. So this is one of the classic cases. Make sure. So it's minus 9s plus 0. So minus 9s over 9s squared plus 1. All right. 1 over s is good to go. What about this last term? What should we do? Yeah, we can factor 9s out. And oh my goodness, there's a 9 upstairs and downstairs. It's almost like it was made to work out. And it wasn't. It just happened that way. Well, you know, you like the happy things. You should look for the happy things in life. All right, 2/3. I'm just copying the first terms down again. E to the minus s plus 1 over s and minus s over s squared plus 1/9. Okay, good. I think maybe we'll, instead of trying to squeeze this in, let's go ahead and add a new page. Okay, so here we go. So, our goal, remember, we're doing this problem, we're trying to find the inverse Laplace. So, we can now say the inverse Laplace of, well, it's 1/9. I know. I apologize. Lots of writing. You don't have to write this much. I'm just writing so that I can follow my work. It's actually pretty useful if you can learn to write so that you can read your handwriting. And I highly recommend it. And I tell that half jokingly, but I am somewhat serious about, on this exam in particular, every semester, if there's any problem that involves a number 5, and it turns out it's one of the top 5 numbers, the number 5. And a lot of people struggle to say, wait, is that an S or a 5? And they just randomly pick. Don't do that. Make sure your handwriting is good enough that you can say, these are S's, or that's a 5. Okay, term by term. Well, the 1/9, that's a constant. We don't need to worry about that. S over s squared plus a 9th. I'll just trust that you have your table. That by itself is a cosine. Cosine 1/3 t. But there's an e to the minus 2s. Okay, so when we see e to the minus 2s, that's something we haven't talked about before. Where does that come into play? So if you ever see e to minus something s, that's an on-off switch has occurred. So it's e to the minus something s says you're going to have an on-off occurring at, so if it's minus a, s at t minus a, and you need to make sure your function also shifts at the same point. All right, so this part here says, oh, we're going to get a u of t minus 2. So we need to make sure that the inside, the cosine, also gets that t minus 2. It's f of t minus a, u of t minus a. Well, the next piece, this is a sine of 1/3 t, but again, there's an exponential. So that's going to tell us the u of t minus 1, but that's going to need to be updating the inside of the sine as well. And we'll talk about what that means. 1 over s is 1. And s over s squared plus the 9th is cosine of 1/3 t. But there's no exponential function, so there's no other shifting. So altogether, what do we have? We have 1/9 times cosine 1/3 t minus 2, u of t minus 2, plus 2/3. sine 1/3 t minus 1 u of t minus 1 plus 1 minus cosine 1/3 t. Just like you thought. Well, maybe not just like you thought, but, you do the work. Take your time. All right, any questions on that one? I feel like that's a good workout. What would the point distribution on the problem look like? It would be out of 10. All problems are equally weighted. There are certain things, it's hard to say because there are certain things I would want to see. I'd want to see expansion happening. So I'd say there's a couple points to expand and break apart. There'd definitely be several points for doing the partial fractions. And some points for, a point for getting this ready. Definitely a point for pulling out the 9, because you need that. And then maybe like 2 points for each piece. So that probably doesn't add up to 10. But I will say this one's probably harder than what you'll see. But we do slightly harder problems, so that when we get to the exam, it could have been worse. That's maybe not the right attitude to have, but at least it's honest. It could have been worse. But, I like this one. It does illustrate some nice ideas. All right, part C. Whew. Okay. So, inverse Laplace log s squared plus 9s over s squared plus 9. And we look on our formula sheet, and we'll look for a long time, but we will never find anything that says natural log. And so we're like, was that a typo that they asked the question? And the answer is no. Because what's happening is they're really pushing us to say, do you know your rules? So which rule is involved? Well, it's this rule. Now you might say, how is that showing up? So let's talk about that rule. So if we have this rule written down in terms of the Laplace transform, Laplace t f of t is equal to, and I'm just copying from my page here, minus the derivative of f of s. Or if you like, it's equals minus f prime of s. So what does that say? Well, it says that when you're taking a t, there's a derivative involved. Now, why does that suggest something to do with logs? Logs are messy, but derivatives of logs are nice. And in particular, derivatives of logs tend to look like the kind of things that we want. So, okay, well, how can we get there? Well, if you take the inverse Laplace of both sides, that says t f of t is minus inverse Laplace of f prime of s. And now our great aha, this f of t has another name. It's the inverse Laplace of f of s. So, the inverse Laplace of a function is negative 1 over t, the inverse Laplace of the derivative. Now, this form is not on the formula sheet, but it's equivalent to the formula we talked about. And so it's nice to know you have it in your back pocket. Essentially, the only time you pull it out is if you see a log, or if heaven has smiled upon you and you see an arctangent. Other than that, you won't pull it out. That's it. That's the only time you pull it out. All right, so how do we use this? Well, it says we're trying to do this inverse Laplace of something messy. So right now our function f of s is log s squared plus 9s over s squared plus 9. Well, so instead of doing the left-hand side, inverse Laplace of f, we'll do the right-hand side, which is do the inverse Laplace of the derivative. So we want to take this derivative, but before we do that, let's use properties of logs. Now notice s squared plus 9s is s times s plus 9. That's what I mean by it'll factor nicely. What can you do with logs? Well, multiplication upstairs becomes addition. Log s plus 9. And then division becomes subtraction. Minus log s squared plus 9. So what is f prime of s? 1 over s. 1 over s plus 9. And this one's a little bit funner. S squared plus 9 downstairs. What goes upstairs? 2s. Chain rule. So we want minus 1 over t inverse Laplace of 1 over s, 1 over s plus 9. And here, I'll pull the 2 over s squared plus 9. So that's minus 1 over t of inverse Laplace of 1 over s, 1. 1 over s plus 9. That's s minus 9. So sometimes you have to think. Plus is minus a minus. So that becomes e to the minus 9t. Then minus 2, inverse Laplace of s over s squared plus 9, cosine 3t. And we're done. I just like that one. It's a fun one. All right. Good. I'd put more energy into A and B in terms of like you're stressing. If you want to stress about something, stress about A and B. Don't stress too much about C. Okay. Well, how are you feeling? Good. Good. Well, in that case, we'll keep going. Don't worry, sooner or later we'll find a problem that goes quickly. Number 3, use Laplace transforms to do the following. So, part A, find f of t, which equals the integral of 0 to t sine of tau cosine t minus tau d tau. Well, there it is. We found it. Oh wait, no. That's not what it means for part A. It's somehow, the implication is that we want to simplify it. Probably so we don't have an integral. Okay, so it says use Laplace transforms. When you see this integral, where are we in our equation sheet? What type of integral are we doing? Convolution. So we say, Laplace transforms works great with convolution. So we have capital F. That's the Laplace of little f, which is the Laplace of this integral. And well, according to our convolution, that's the Laplace of the two functions, namely sine convoluted with cosine. And to do that, because the convolution says, well, take sine, that, and multiply it by the Laplace of the cosine. Do we know the Laplace of sine? Yeah. 1 over s squared plus 1. Do we know the Laplace of cosine? Yes. S over s squared plus 1. So that is currently s over s squared plus 1 squared. Right? Multiply the tops, multiply the bottoms. Now, we look at our formula sheet and say, well, golly. I feel like I'm in a 1950s sitcom there, golly. And say, well, is there anything that looks like s squared plus 1 squared? All right. Ooh. Ooh. So, there are things that look like s squared plus 1 squared. In fact, there's a pair of them. Namely, the t sine bt, t cosine bt. So, which one are we trying to match right now? We're close to the sine, right? Because that's basically, we have the s squared plus 1 squared. What are we missing? 2b, or not 2b. Well, no, it's 2b, right? But what is b? 1. So what do we need upstairs? 2. So we'll put a 2, and of course, if we add, we have to balance, so times a half. And now our great aha. We know how to take the inverse Laplace. So our answer, f, it's the inverse Laplace of this 1/2 2s over s squared plus 1 squared, which is 1/2 times t sine t. And that was not too bad. We didn't have to look in some old trig book to say, how do we handle cosine t minus tau? We didn't have to multiply it out, didn't have to use power reduction, didn't have to do anything crazy. The nice thing is Laplace transforms did all the heavy lifting for us. So that's cool. All right. Part B. Find f of t, given that f of t equals 2 integral 0 to t f of t minus tau e to the minus tau sine tau d tau plus e to the minus t cosine t. Well, all right. How do we start? Well, probably we should use Laplace transforms. They might say, how do you know that? It says it. The problems are pretty good about telling us what they want us to do. We just have to hear it. All right, so we'll take the Laplace transform of both sides. So we have f. We get the 2. What do we see here? It's another convolution. So when you spot a t minus tau and something with tau, you're doing convolution. So you have f is one of your pieces. What are we convoluting it with? E to the negative t sine t. Yes? All right. So Laplace transform says you put an f. And then you say, okay, what's the Laplace transform of e to the minus t sine t? Well, we know how to do sine t. That's 1 over s squared plus 1. What does the e to the minus t end up doing? It's a shift, right? So in particular, this would be 1, and instead of s squared, it's s minus 1. So s plus 1 squared plus 1. All right. Similar thing happens. Laplace transform of e to the minus t cosine t. We're going to have plus s plus 1 over s plus 1 squared plus 1. So it's the Laplace transform of cosine, but everywhere where you see an s, you put an s plus 1. So far, so good? What happens next? Box it? No. We're not even close to that. Oh, to live the dream. To be young and to think that boxing is easy. Well, yeah, we're trying to find f of t, so now we should try to find capital F. So, okay, so what do we have? We have capital F. One of those Then we have minus, well, 2 over, and if you multiply this out, that's s squared plus 2s plus 2. Yes, s squared plus 2s plus 2 equals s plus 1 over s squared plus 2s plus 2. All right, algebra. What do we do here? Combine, common denominator, s squared plus 2s plus 2. So s squared plus 2s plus 2 minus 2 over s squared plus 2s plus 2. And that's times f equals s plus 1 times s squared plus 2s plus 2. Well, what can we do? Simplify, sure. We can cancel some 2's. We can even say, since these are both on both sides in the same place, those will actually cancel as well. So what do we have? We have that capital F is s plus 1. Now divide that by s squared plus 2s. So we're pretty close. What comes next? Sorry, what? Ooh, Laplace inverse. But what happens before Laplace inverse? We'll first do some partial fractions. Now, if you're pretty good with your Laplace inverse and you happen to have memorized the Laplace of Cauchy and the Laplace of Synge, you're actually almost there. But probably we didn't memorize that. And it's not on the table. So we'll just do partial fractions. All right. Well, we always need more practice with partial fractions. That's s times s plus 2. We'll do it a little bit quicker because I know you're like, I've seen so many partial fractions now. There's no partial fractions problem that can trip me up. S plus 1 equals a times s plus 2 plus b times s. We make good choices like s equals 0, 1 equals 2a, or a equals a half. S equals minus 2, minus 1 equals minus 2b, or b equals a half. And so we can say, this is the same as a half, 1 over s, plus a half, 1 over s plus 2. And now we're ready for the Laplace inverse. So f, which is the Laplace inverse of big F, is 1 half times the Laplace inverse of 1 over s, which is 1, plus 1 half Laplace inverse 1 over s plus 2. Well, that's s minus minus 2, which becomes e to the minus 2t. So 1 half plus 1 half e to the minus 2t. Yes? Good? Did I make a mistake?
No. The 2 capital F, I don't... Where is that coming from?
This part?
No, all the way up there in the purple.
Oh, I'm taking the Laplace of both sides. So usually lowercase f is our function of t. And then so if you see lowercase, think of that as a t piece. And uppercase, think of that as after you've done the Laplace. So like capital F is the Laplace of little f. Like capital X is the Laplace of little x, so forth and so on. So I was skipping a step in writing. All right. Good. Well, I should try to pick up my pace a bit. Number 4. Find the Laplace transform of f of t, where f of t is t squared if we're from 0 to 2, 4 if we're between 2 and 4, 20 minus 4t if we're between 4 and 5, and 0 if we're from 5 to infinity. What kind of function is this? This is piecewise. All right, good. So we know how to handle piecewise functions. Now, you don't need to do this, but in case you're wondering what does this function look like, and again, you don't need to do this, what we see is that it follows a parabola, it plateaus, goes straight down, and then runs from 0. It happens to connect. Again, you don't need to know that to answer the question. Because the picture is not what you feed into the Laplace transform. Nor is this what you feed into the Laplace transform. What do we need? Well, for piecewise, you need to take advantage of your on-off function. And so you want to know how to rewrite a piecewise function. So, how do we write a piecewise function? We start at the very beginning. It's a very good place to start. It starts as t squared. Great. Where's the first time we change? 2. So we're going to have an on-off switch at 2. So we add a u of t minus 2. So at this point, we're going to turn on the 4. So I have a plus 4. Turn off the t squared. Subtract t squared. Where's the next change? 4. So we have u of t minus 4. And what are we turning on? 20 minus 4t. What comes after? What are we turning off? The 4. What came before? All right, where's our next change? 5. So we have on-off at 5 happening. What comes after 5? 0. What comes before 5? 20 minus 4t. All right. Now we're getting closer to being able to plug this in. We're not ready yet. At least we don't think we are. We're going to go through piece by piece and say, all right, are we happy with this? The t squared, are we happy with that? Yeah, great. We love it. 4 minus t squared. Not quite, yeah. What's the problem? Yeah, you have to Q off of the t minus 2 in the front of it. So you say, okay, well, unfortunately, 4 minus t squared is not in terms of t minus 2. So we're going to do a little bit of work here. But not too bad. We're not going to be super crazy. We're just going to say, well, t, here's how I like to do it, is t minus 2 plus 2. True story. T is indeed t minus 2 plus 2. But the thing is, I want there to be t minus 2's. So let's expand this. So this is 4 minus t minus 2 squared plus 4 times t minus 2 plus 4. Yes? If you just expand t minus 2 plus 2 squared. And now clean it up a little bit. Well, notice you have a 4 minus 4. Those cancel. So it's minus t minus 2 squared minus 4 t minus 2. Ah, that parentheses, very important. Use parentheses. I know I say that a lot. Because they are. I want you guys to get all the points. More importantly, please don't take the final. Please. It would make my life so much easier if I didn't have to grade it. But anyways, my selfish reasons aside. Are we happy now? Yeah, because we have this function, which is attached to u of t minus 2, is in terms of t minus 2. Okay, moving on. 20 minus 4t minus 4. Are we happy yet? No. But maybe we're close. This is the same as 16 minus 4t. What can we do? Pull the negative 4 out, and this becomes negative 4 times t minus 4, and we're happy, right? Because we match the t minus 4 and t minus 4. Okay, how about here? The last leg of our journey. Well, if you distribute this through, this is minus 20 plus 4t. What can you do there? Pull out a 4, and this becomes t minus 5. And we match. All right. So I'm going to rewrite f one more time, and then we'll work the answer. So we have t squared, and then I'll have, well, I'll put a minus, and I'll write the function in front. t minus 2 squared plus 4 t minus 2 u of t minus 2 minus 4 t minus 4 u of t minus 4 plus 4 t minus 5 u of t minus 5. All right. So, the Laplace of f of t. Okay, t squared. Well, good news. That's on our formula sheet. T squared. That's 2 factorial s to the 2 plus 1. So that would make that 2 factorial is 2 and 2 plus 1 is 3. So 2 over s cubed minus the u of t minus 2 tells us we're going to have an e to the minus 2s. So we're coming back to our rule. If we ever have u of t minus a, f of t minus a, we're going to have an e minus 2s. So the minus 2 inside the u of t minus 2 matches that minus 2 up in the exponent e to the minus 2s. Now we have to be ever so cautious. So oftentimes we don't write this down explicitly, but we should really think of this as t squared plus 4t. So in other words, think about what's being attached to that. Right now we've written in terms of t minus a. Rewrite it as though t minus a became t. Does that make sense what I'm doing right now? What does t squared do? Well, the answer is it's what it did over there. So it's 2 over s cubed plus 4. And what's t? Well, that's similar 1 over s squared. All right. Now, minus 4. Okay. U of t minus 4, e to the minus 4s. This t minus 4, we say, think of this as t. And so, the rule for t is 1 over s squared. And the last part, 4, u of t minus 5, e to the minus 5s. And then we say, okay, think of this t minus 5, replace t minus 5 by t. And so it becomes just the function t. You say, well, we know how to handle t. We've done it a couple times. It's 1 over s squared. And now, we're done. That's the answer. So if you see a piecewise function, you say, okay, figure out your on-off switches, rewrite as needed, and then once you've rewritten, take the transform and know how to apply the rule. So piecewise should not make us nervous. Any questions?
For the part written in green, the intuition of being able to rewrite that, just how...
This part?
Just from the 4 minus t squared to 4 minus and then the parentheses, how did you create that? And when you're spanning it out, so you make it through?
Well, okay, so the key here, how did this come to be? Well, I said I have to rewrite, so what I'm going to focus on is everywhere where I see t, I want it to look like t minus 2. And so I say, well, I'll make my t look like t minus 2. But if I add a t minus 2, if I immediately add a 2 after, t minus 2 plus 2 is indeed t. But now I'm just going to always keep that t minus 2 as something, and then do the algebra that follows from that. Anything else? All right. Well, on to, an essay. Great. So, I haven't done this problem. I wrote it. I'm a little nervous. I don't know if it has a nice answer. We'll find out. A 20-gallon tank is full of brine, also known as salt water. And brine is entering and leaving the tank at a rate of 5 gallons per minute. Okay, well that's good. Maybe we should update and add a picture here. So we have a 20-gallon tank. We have water in, water out. Well, brine in and brine out. Now the good news is that our in and out matches, so our tank neither loses nor gains. It's always 20 gallons. So that's going to make things a little easier. Now we're told, between times 0 and 2, the concentration of salt coming in is 2 ounces per gallon. At time t equals 2, an additional 12 ounces of salt is dumped into the tank, and the concentration for salt coming in is reduced to 1 ounce per gallon. Okay, so there's a lot going on here. That sentence is like half the problem. So this is telling us about what's happening. So let's set up our equation. So x of t is the amount of salt. I'm reading ahead. So given that the tank initially has 10 ounces of salt at time t equals 0, which is another way of saying x of 0 is 10, and x of t is our amount of salt, and we want to solve for x of t. So let's talk about x prime, because we know how things are changing. We have things coming in, things going out. That's change. So change, we take our in minus our out. Now our out is pretty straightforward. How much of our salt do we lose? So think of it this way. We're 5 gallons per minute of a 20-gallon tank leaves. So how much of the brine leaves? What ratio of the brine? 1/4, right? So 1/4 of the brine is leaving all the time. So our out is 1/4 x. You can think of it as, if you don't like the 1/4 x, our flow rate is 5. Our concentration is x over 20. So 5 times x over 20 is the same as 1/4 x. Okay. So that's the straightforward part. I'm going to move that across. So we have that x prime plus 1/4 x is our in. This long sentence in the middle, that's the in. So let's talk about what's happening. From time 0 to 2, we have one behavior. The concentration is 2 ounces per gallon. Then at time 2, we dump in salt and we change the concentration. So let's be a little bit careful here. This 12 ounces of salt that's dumped into the tank, how do we model that in terms of the tools that we have available to us? It's the delta, because it's just a one-time event, an instantaneous thing that happens. It's not a sustained thing, it's just one and done. Okay, so that says that we're going to have 12 delta, and because it's time t equals 2, t delta, not equals. Okay, let's try that again. 12 delta t minus 2. Okay, all right. So that's just for the salt that gets dumped in. What about the rest of it? Well, the rest of it, we have, it's coming in from the flow. So it's the flow rate is 5. What's the concentration? Well, it's 2 ounces, and then it's 1 ounce. So how do we model that? Using it's a piecewise, it's a step function. So it's going to be 2 subtract u of t minus 2. Yes? Because before time 2, the step function hasn't turned on yet, so it's just 5 times 2, which means there's 10 ounces per minute coming in. After time 2, this turns on, it's 2 minus 1, which is 1. So that tells us then we have 5 ounces per gallon coming in. Oh, sorry, 1 ounce per gallon, 5 gallons per minute, so there's 5 ounces per minute coming in. Excuse me. Oh my gosh, got my units wrong. I should start paying attention to units. No. That would make me a physicist. I don't want that. Okay, all right. So that's the differential equation. Now that's not our answer, but I just want to say we made a lot of work to get there. All right, so do you agree with the setup? Because if you don't, then everything after this will not be as exciting. All right, seeing no objections, what's the next step? Well, anytime you have a delta or a u, you really should do Laplace transform, and we should do Laplace transforms. Okay, so to solve this differential equation, we take the Laplace transform of both sides. So the Laplace transform of x prime plus 1/4 Laplace transform of x equals 12 Laplace transform of delta t minus 2 plus, and you can distribute this through if you want, plus 10 Laplace transform of 1 and minus 5 Laplace transform of u of t minus 2. Okay, so do we have something that helps us with these things? Well, yes. Near the bottom is the part when it comes into differential equations. So if I want to take the Laplace transform of a derivative, I essentially add s, but I need to subtract some initial condition. If I had a second derivative, which I don't here, but there's always more problems, it would be an s squared and more initial conditions. So in our case, this first term would become s capital X subtract our x0 plus 1/4, and then we have our capital X delta. Well, that's on our formula sheet. That's up here, delta t minus a. So delta t minus a would be, in our case, e to the minus 2s. And Laplace of 1 over s. And Laplace of u of t minus 2, well, that's actually on our formula sheet as well, right next door to the delta. So u of t minus 2 would be e to the minus 2s over s. All right. Well, what do we do now? We plug in x of 0, which is given to us. It's 10. And what comes next? Yeah. In particular, our goal is to solve for x. So the principle at play is that we're solving a differential equation using Laplace transform by turning it into an algebra problem. In this case, the algebra problem solve for x. But the real algebra problem is make it nice so that we can do inverse Laplace. So we have s plus 1/4 capital X. We'll move the 10 across. That's 10 plus 12 e to the minus 2s plus 10 1 over s minus 5 1 over s e to the minus 2s. Or capital X is 10 s plus 1/4 plus 12 e to the minus 2s over s plus 1/4 plus 10 1 over s times s plus 1/4 minus 5 1 over s times s plus 1/4 e to the minus 2s. Yes? Okay. Well, what are we going to need? Partial fractions. Now, do we need to do partial fractions for the first part? No, that's great news. Do we need to do partial fractions for the next part? No, we don't. That's actually well set up. Now, here we have to do partial fractions, and here we do have to do partial fractions, but what do you notice? It's the same thing we're doing. Oh, it's like they wanted us to save time. Okay. All right. So, off to the side. 1 over s times s plus a fourth. All right. Well, hopefully by now you're comfortable with partial fractions. So I'm not going to say everything out loud. A over s, b over s plus a fourth. You clear your denominators. So you'll get 1 equals a s plus 1/4 plus b times s. And of course, that came from multiplying out. Make ourselves some good choices. S equals 0 says that 1 equals a fourth times a, or a equals 4. S equals minus a fourth. 1 equals minus a fourth times b, or b equals negative 4. All right. Well, we've run out of space, but don't worry. We have more paper. I splurged and got more paper for today. So, updating. What do we have? Our function capital X, not the function we want, but the Laplace of the function we want. 10 times 1 over s plus a fourth. Plus 12 e to the minus 2s over s plus 1/4. Plus 10, and now we'll use our partial fractions. So that's 4 over s minus 4 over s plus a fourth minus 5, and that'll be 4 over s minus 4 over s plus a fourth e to the minus 2s. Okay, good. Whew, the end is near with this problem. All right, are we ready? Yes? No? Maybe? I think we can probably do it. Should we go for it? Sure. I like that attitude. Yeah, maybe. All right. Cool. So, our amount to solve. Inverse Laplace of big X. First part's not too bad. We have the 10. And the 1 over s plus a fourth becomes, that looks like an exponential. So it becomes e to the minus 1/4 t. Now, e to the minus 2s over s plus a fourth. What's that going to do? Well, we'll be careful. There will be a u. So anytime there's an exponential, it's a u. There's a u involved. So we have s plus a fourth, e to the minus 2s. The 12 will do what? Yeah, it's going to be a constant. The e to the minus 2s tells us on off, u of s minus 2. And now you say, well, what's this function? Normally, by itself, this would be e to the minus 1/4 t, just like it was over here. Oops, I wrote s minus 2. This should be t minus 2. My apologies. But what will it become? Yeah, e to the minus 1/4 t minus 2. Okay, so continuing on, we have plus 12 e to the minus 1/4 t minus 2 u of t minus 2. So this is not too surprising. This essentially says the 10 ounces of salt that were in there initially are slowly going out. This one says the 12 ounces of salt dumped in at time 2 are slowly going to go out. So that's good. Okay, so the next term, well, we can factor a 4 out. So we could say plus 40. And then if we factor the 4 out, so 1 over s would be 1 minus, then here, e to the minus t over 4. Similar, we can factor 4 out. Minus 20. Okay, now what happens? Well, we have that e to the minus 2s. And so that's going to become a u of t minus 2. That's terrible, but that's okay. 1 over s would normally become 1, but we're going to shift it. So now it's 1. Yes? In fact, we're really just doing the same thing we did over here. So the 1 is 1, but this e to the minus t over 4 is really now e to the minus t minus 2 over 4. So just as we had over here, it's the same reason. It's that shifting going on. Now what do we do? Yes, yes, quick, box it before anybody says, wait, no. Yeah, no, that's the answer. See, that wasn't so bad. So, as far as story problems go, there's 2 camps. There's the one we just did, which is mixing, and there's the spring problems. So make sure you're ready for both. So that's why we're doing 2. We did our mixing one, now a spring one. So a mass spring system is set up with a mass, m equals 1, a damper, c equals 6, a spring constant of k equals 25, and an external force consisting of an instantaneous pulse to the system of 12 at time t equals 5. Given that x of t is the displacement, which is just a fancy way of saying motion of the spring, and that we have initial conditions x of 0 equals 4, x prime of 0 equals 8, solve for x of t. So you'll notice they don't give you the differential equation. So make sure you know how to set it up. So as a reminder, how do mass spring problems work? Well, you get m x double prime, this is your mass, plus cx prime, this is your damper. Not all of them have damper, some do, some don't. Kx, this is your spring constant, equals, and over here is your external force. So it's just a matter of plugging in what they give you. So in our case, we are given the following. Mass is 1, x double prime, damper is 6, 6x prime, spring constant is 25. So 25x. Our external force. Well, there is an external force, and it consists of an instantaneous pulse. So we see instantaneous pulse. We say delta. And we need to know 2 things. How big is the pulse? So that's the 12. When did it happen? That's the time. So 12 delta t minus 5. And we also write here, just for reference, x of 0 is 4, x prime of 0 is 8. So there's the setup. This would be a good chunk of the problem. So I'm going to box, that's not the final answer, but I just want to say we've gotten to a good place. We should celebrate our milestones. Oftentimes problems are just a series of smaller problems. And every time we get a smaller problem done, we should be happy with that. Now, what comes next? Take the Laplace. So take the Laplace of everything. So the Laplace of x double prime plus 6 Laplace x prime plus 25 Laplace x equals 12 Laplace delta t minus 5. And I can already see that, a classic case of 5. So we'll have to pay attention to make sure our 5s look like 5s and our s's look like s's. So we're going to use our rules for taking Laplace of functions, derivatives of functions and second derivatives of functions. And also we'll use our rules for taking Laplace of delta. So for x double prime, this will be s squared capital X minus s x of 0 minus x prime of 0 plus 6 parenthesis s capital X minus x of 0 close parenthesis plus 25 capital X equals 12, and the Laplace of delta is an exponential function e to the minus 5s. Okay. All right, good. Well, now you plug in initial conditions. So the Laplace transform, when you're solving differential equations, initial conditions come at the start, not at the end. So x of 0 we know is 4. X prime of 0 we know is 8. And we gather. So we're going to gather everything which has a capital X attached to it. There's 3 terms. So s squared plus 6s plus 25 capital X. These coefficients should look suspiciously like our differential equation. In fact, they should be exactly like that. And if it's not, well, let's look for our error. But we're okay in this case. The pieces that don't have a capital X will move across. So here we have a minus 4s. So that will come across as a plus 4s. Here we have a minus 8 and a minus 24. Right? Because 6 times 4. So minus 8 minus 24 makes minus 32. So this will become a plus 32. And then plus 12 e to the minus 5s. All right. Well, s squared plus 6s plus 25, does it factor? No. So if it doesn't factor, what do? Complete the square. So s squared plus 6s, what would we want to add to make this a very nice square? Add 9. Okay, but we have plus 25. Well, that just means we have 16 left over. So that says that the term in front of the x is really s plus 3 squared plus 4 squared. So I'm going to divide, move it across. And I'm going to move it, and I'm going to really do it in 2 pieces. I'm going to have it, the 4s plus 32 is one part, the 12 e to the minus 5s is another part. The reason I just want to separate these is because the part with the exponential function, I'm going to have to do something different. That's going to have a u involved. And I don't want that to be attached to the rest of it. So what that says is that our function capital X looks like 4s plus 32 divided by s plus 3 squared plus 4 squared plus 12 over s plus 3 squared plus 4 squared e to the minus 5s. Okay. Well, which part do you want to talk about first? 4s plus 32. Okay. Now, looking at this, we see the s plus 3 downstairs. We say, okay, we're locked in. We're committed to having things look like s plus 3. So we say, well, that means we want the stuff upstairs to look like s plus 3. So we say, well, that's okay. We can do that. In fact, that's not so hard at all if we think about it. We'll just say, make it a 4 times s plus 3. Like, oh, okay. But wait, hold on. We're supposed to have a plus 32. This is plus 12. So what should we do? So plus 20. Does that make sense? I want, because this is s plus 3, I want the top to look like s plus 3. So I just say, oh, okay, replace the s by s plus 3, and then make the numbers work. So it's equal. Now, the nice thing is we don't have to worry about that here. I'll save that for in a minute. All right. So now let's pull this apart. So this is really 4 s plus 3 over s plus 3 squared plus 4 squared plus 20, 1 over s plus 3 squared plus 4 squared plus 12, 1 over s plus 3 squared plus 4 squared e to the minus 5s. Are we happy with the first term? Yeah, that's actually, we're in a pretty good space. So this is, we're happy. Well, there's some things to talk about, but we're pretty happy. The second term, are we good to go? If we're not, what should we do? We want a 4 upstairs because we want it to look like the b over s squared plus b squared kind of thing. So if we put a 4 upstairs, we can do that, but we put a 4 downstairs. Are we happy now? Yes. Well, that trick was so nice, let's do it twice. Put a 4 up, put a 4 down. All right, now are we happy with this part? Yes, life is good. All right, so we're ready to say, what is our motion, little x? Inverse Laplace of big X. Okay, so for the first term we have a 4. Because we have s plus 3, what does that tell us about our solution? There's a shift, so shift on the s side becomes what on the t side? So shift on the s side means exponential. So there's an exponential. Which e to what power? Positive 3t or negative 3t? Negative 3t. So s minus minus 3. Now, if you imagine that instead of s plus 3, you just saw s over s squared plus 4 squared, what function is that? Cosine 4t. 20 over 4 is 5. Then this will become similar, e to the minus 3t, because of the s plus 3, sine 4t. Plus 3, the 12 over 4, e to the minus 5s, says we have an on-off switch at 5. We should expect an on-off switch at 5, because something happened at 5. So we should anticipate. If we see a delta at a time 5, that means an on-off switch will happen at time 5. What's the function? Well, normally it's this e to the minus 3t sine 4t. Is that what we write here? And what do we write instead? Yeah. So it's like the e to the minus 3t sine 4t part, but we have to shift. So e to the minus 3 t minus 5 sine 4 times t minus 5. And what happens next? Yeah, we're done with this problem. Whew. At least we fit it on a page. Progress. That's good progress. All right. So that's winds down the Laplace transform part, which between the two sides, the Laplace transform is the part that most people get nervous about. So now we're going to go into series, which initially when you hear series, you're like, oh, but then you're like, oh. it's not quite so bad. So what happens with series? So the philosophy is it's a lot of comparing coefficients at the end of the day. So let's look at this problem, number 7. We're given that we have a series solution to our differential equation, y double prime plus 1 minus 2x squared y prime plus 3xy equals 0. And we have some initial conditions. Y of 0 equals 1, y prime of 0 equals 4. And we're asked to find a recurrence relationship for the coefficient Cn. Make sure to include when the relationship is valid. And find a couple of terms. Oh, whoops. This was my notes for how to write what problem I wanted to write here. That's not part of the problem. I know. I should have caught that. But that's good. That's less for us to read. Okay, so how do these problems work? When you see recurrence relationship, it always means the same thing. You're putting everything into one big sum. That's what your goal is. One sum. So how do you get things into one sum? Well, there's a couple things you do as prep. You might need to do a little bit of expanding. And what do I mean by that? Well, what I mean is this middle term. So instead of writing it as 1 minus 2x squared times y prime, multiply that out. So it's y double prime plus y prime minus 2x squared y prime plus 3xy equals 0. So that's what I mean by expanding, okay? Because we want to, the goal here is to work and get all the powers of x together that are the same. And since the 1 and the x squared have different powers, we want to separate them. After we've done our expanding, we're going to replace our y prime, y double prime by our series. And so we'll do that in a second, because then comes the fun part. It's our 3-step process, and this is how I like to think of it. We're going to shift so all our powers agree. We'll peel off any terms at the start that we need to, and then we combine. And we have our one sum. All right, so here we go. Y double prime. We have y for reference, so what is y double prime? Well, you just take derivatives term by term. 0 to infinity n minus 1, cn x to the n minus 2. So I took two derivatives. First time I took derivative, n comes down. And then it's x to the n minus 1. Second time, n minus 1 comes down, x to the n minus 2. So this part is the y double prime. Plus y prime. Sum n equals 0 to infinity, n cn x to the n minus 1. All right. Minus 2x squared y prime again. There's a bit of writing here. So it's just be patient. Give yourself a chance to double check. Did you copy everything right? Did you take your derivatives right? And, all right. So I started with our differential equation, and I replaced y prime, y double prime by the corresponding series pieces. All right. Now, before we go to doing our shifting, there is something that has to happen first, which is these powers of x in the front. They need to go in. All right. I will rewrite it all again. I know. I feel the same way. You probably don't have to, but I just want to do it just so you can see it in slow motion. If you can follow your own work, and you're like, I can do this. I know how to read my own handwriting. and I can go back and double check and I'll know exactly what happened, then it's okay if you don't do that. But all right, so I just moved the x's inside. So let's talk about our shifts. In our first sum, what's our shift? Well, n minus 2 becomes our new exponent. Pick whichever symbol you like. I like L. You don't have to like L. I, J, K. Those work too. Somewhere near to the middle of the alphabet. Now you might say, why the middle of the alphabet? Mathematicians have been bred that way. Certain parts of the alphabet represent different things. So like our variables are towards the end, X, Y, Z. Time, or T, maybe S. Constants at the beginning, A, B, C. And so indexes for sums are in the middle. So that's why I, J, K, L, M, N, somewhere in that range. So it's not hard to figure out the shift. Just say, what's the power of X? And I just want to make that power of X my new power. All right. So we remember our rule of substitution, which is update everything. Not just the one part you like, everything gets updated. So this becomes the sum, and if you plug in n equals 0, so that starts from -2 to infinity, and n is L plus 2, so L plus 2 times L plus 1, CL plus 2, x to the L. If you didn't have to write too much, you probably would think these problems were really fast. And that's kind of true. A lot of it's just that you have to write. And so take your time. So the middle sum, L equals -1 to infinity, L plus 1, CL plus 1, x to the L, minus 2. Then we have sum L equals 1 to infinity. And we're going to have L minus 1, CL minus 1, x to the L, plus 3, sum, and when you plug in n equals 0, you get L equals 1 to infinity, C, L minus 1, x to the L. All right. All the powers are agreeing now. So that's what the shift does. Let's talk about peel. When we peel, we want to get a common start. What start are we shooting for? As I point to the answer. 1. Why 1? Well, because that's the highest of the starts. There's a -2, there's a -1, there's a 1 and a 1. So let's talk about the first thing, our first sum. When you plug in -2, what do you get? When you plug in -1, what do you get?
0.
When you plug in 0, not 0. Okay. All right. So when you peel here, this part, well, you're going to have the L equals 0 term, which is 2 times 1 times C2, so 2C2, plus everything else. 1 to infinity. I'll just put ... For this term, plug in -1, what do you get? 0. Plug in 0, you don't get 0. You get 1, C1. So you get C1 plus other stuff. And then these are fine. We don't have to do anything. All right, so we're a lot closer than you think. We've figured out how much we have to peel. So at this stage, we have the following. We have the stuff we pulled off, so that's 2C2 plus C1 plus one big sum, L equals 1 to infinity, of L plus 2 times L plus 1, CL plus 2, plus L plus 1, CL plus 1, minus 2, don't forget about coefficients in the front, times L minus 1, CL minus 1, plus 3, CL minus 1, x to the L. Okay, and all of that equals 0. And if you're wondering where does equal 0 come from, this is the y double prime plus y prime minus 2x squared y prime plus 3xy. That's this expression if you plug in y as your sum. And that equals 0. Okay, so how do you find the recurrence relationship? Well, you go into your sum. It's that piece. That's the recurrence relationship. So we'll write it down, our recurrence relationship. It's a big one. It's L plus 2, L plus 1, CL plus 2, plus L plus 1, CL plus 1. And we can combine these last two together. Let's do that. So this would be minus 2L plus 2 plus 3. So we could write this as 5 minus 2L CL minus 1. And term by term, it has to equal 0. Because two polynomials are equal if and only if the corresponding coefficients are equal. Well, the right-hand side is the polynomial 0, where all the coefficients are 0. So all these coefficients have to be 0. Now that's the recurrence relationship. It does say, make sure to include when the relationship is valid. Oh, when is this relationship valid? Look at the sum. This is valid for L greater than or equal to 1. All right. Whew. Now, I'll show you two things. Will you see a recurrence relationship problem? Yes. Will it be this bad? No. And you're probably thinking, like, this wasn't bad. Oh, well, in that case, no, it won't be this bad. All right. Are we done? No. What else do we have to do? Yeah, find your constants. Sorry, find some of your coefficients. Well, some coefficients are freebies. So how do you find your freebies? You use your initial conditions. And our y of 0 is C0. Well, we know what y of 0 is. It's 1. Our y prime of 0, that's our C1, and that's 4. Okay, so those are freebies, initial conditions. So that gives us 2 out of the 5. And even if nothing else, you write down initial conditions, you're guaranteed at least 1 point. So if this is all you can remember, that gives you 1 point. You're only 9 more points away, and then you got the whole problem. All right, where does the next come from? Well, now we start looking at the coefficients. So how do we find our next term? We come to here. This is our constant term. Now, our constant term behaves slightly differently. That's why it's outside the sum. It has a slightly different form than the recurrence. So we have to treat it differently. That's why it's not part of the recurrence. But it still is true that it's 0. So we know that 2c2 plus c1 equals 0. But do we know anything about c1? Yeah, we know c1 is 4. So 2c2 plus 4 equals 0. So what's c2? Negative 2. All right. We're now up to 3 coefficients. And we don't need to see that. We can move this up. How do we find our next coefficient? We come into our coefficient of x, which is L equals 1. So we're going to plug in L equals 1. 3 times 2 times C3 plus 2, C2, plus 5 minus 2, which is 3, times C0 equals 0. So I'm plugging in L equals 1 into the recurrence. Well, we should know everything except C3. So we have 6C3, 2C2 is minus 4. 3C0 is plus 3. Yes, 3C0, 2C2. So what does that tell us about C3? 6C3 equals 1. C3 equals 1, 6. Good. One more to go. Okay. What do? Plug in 2. 2 plus 2 is 4 times 3 times C4. 2 plus 1 is 3 times C3 because we're at 2. 5 minus 4 is 1. C1 equals 0. Okay, so 12C4 plus 3 times C3. Well, C3 is a 6, so 3 times that is a half. 1 times C1. Well, C1 is 4. So plus 4 equals 0. 4 plus a half. What's another way to say that? So 4 is also 8 halves. 8 halves plus 1 half is 9 halves. So 12C4 equals negative 9 over 2. So C4 is negative 9 over 24. But can we simplify? You can pull out a 3. Negative 3 over 8. So our answer, C0 is 1, C1 is 4, C2 is negative 2, C3 is 1 over 6, C4 is negative 3 over 8. Whew. Good. Good. The process is not bad. It's just be careful. Don't rush. You'll be all right. All right, shall we try another problem? Haha, too bad, we're doing it anyways. Number 8. Given that y, they changed the index just to play with us. Now it's j. Now, changing it from n to j does what? Nothing. Very good. I'm glad you got that. So the sum cj x to the j is a solution to y double prime plus 2y y prime plus 4xy equals 2 over 1 plus 3x, y of 0 equals 1, y prime of 0 equals 4. Find C0, C1, C2, C3. Now, what do you notice is conspicuously missing from this? Recurrence relationship. This is good news. Recurrence relationship makes it harder. We don't have to do that. We just have to grab the terms at the start. And actually, we can do several things pretty quickly. What do we know about C0? Yeah, it's y of 0, it's 1. And C1? Y prime of 0, which is 4. Which means we're halfway done before we even started. 1 point. No, it's not 5. Unfortunately. It turns out C2 and C3 are harder. And so it's more points. Now, how do we get these? So this is important. So to get C2, we're going to look at the coefficient of what? Coefficient of 1. The constant. The initial conditions gives us the start. The next thing will come from the constant coefficients. The one after that, where's the C3 going to come from? It's going to come from the coefficient of x, which means I just have to figure out what's happening with my constants and what's happening with my x's. I don't care about anything past x. x squared, that would be if I wanted to look at C4. I don't want to look at C4. Because my goal is to finish this problem and give myself lots of time to check my work. Maybe go back and admire some of the other problems. So, all right, with this in mind, we say, okay, our mindset is every piece is going to become a polynomial. So that's the game. When we're talking about series, everything's polynomial. And we're just looking at enough of our polynomial as to say what's happening with our constant, what's happening with our x. So, make some notes. We'll start with the y. I'm just going to, just for notes, y is the sum, 0 to infinity, cj, x to the j. I'll write down y prime as well. 0 to infinity, j, cj, x to j. Don't worry, I'm not going to write down many sums. Our goal is to write down very few sums. J minus 1. J minus 1. Cj, x to the j minus 2. All right. Good. Good. We know how to handle y double prime. Y prime. X we're okay with. X is polynomial. Series are polynomials. So anything polynomial is great. 2 over 1 plus 3x. Can we handle that? Remember, polynomial. Is that a polynomial? Or is there something that we can use to make it a polynomial? So be ready to look in the lower corner of your formula sheet. So, 2 over, 1 plus 3x? Yeah, 1 plus 3x. 2 over 1 plus 3x. It looks like geometric. So pull out the 2, 1 over 1 plus 3x. What does it behave like? If we write it as a series, and if you don't want to, you don't have to get away, have to. What's the power? Something to the k. What goes into the inside? Minus 3x. Why minus 3x? Because you need to have 1 minus something. That's 1 plus something. But of course, as we know, our classic plus is just 2 minuses that haven't gone close yet. All right. So, here we go. Y double prime is, what's our constant term? Well, how do you get x to the 0? Plug in 2, right? 2 minus 2 is 0. So it'll be 2 times 1 times c2. So it's 2c2, that's the constant term. What's the x term? 6 c3x, and we don't care about the rest, so ... Plus 2 y. Well, c0 plus c1x ... y prime. The first time is j equals 1. That would be c1. And then next would be j equals to 2c2x. And then ... plus 4x. Okay, how much of y do I need? I could put c0 plus c1x. Do I need all of that? I can actually just stop at c0. Why? Well, because I'm already up to x when you multiply the x in. Equals on the other side. So, what's the first term look like? Plug in k equals 0. You get 1, and don't forget times by 2. 2. What's the next term look like? Negative 6x. And then? We don't care. Now, believe it or not, everything we need to finish the problem is there. We just need to extract it. How do we do that? We gather. So, how can we get our constants? Well, we go through and look for constants. 2c2, that's a constant. And now, the next term, the only way I can get a constant would be 2 times the constant plus 2c0, c1. No constant there. So that's the constant on the left. That has to match the constant on the right, which is 2. Plug in what we know. What do we know? We know c0, c1. Everything, by the way, has a 2, so let's just go ahead and get rid of that. So c2, c0 times c1 is plus 4 equals 1. So c2 is negative 3. All right? Are we ready for the next part? Coefficient for x. 6c3, good. Now here, we could do 2 times c0 times 2c2, which would make this plus 4c0c2, or 2 times c1 times c1. So that would be 2c1 squared. So you have to look at all ways you can multiply and get an x. What else? 4c0. And all that equals negative 6. Coefficient on the left for x has to match coefficient on the right for x. Do you see the game? We're comparing coefficients. Can you play this game? And if you can't, you have till Thursday to figure it out. No pressure. Thursday's a long ways away. Imagine it was what was 4 days ago? Well, however many days ago. That's how many more days you have. Plenty of time. Okay, so, well, we plug in what we know. C0, we know is 1. C2, we just found that. That's negative 3. 4 times 1 times negative 3 makes minus 12. C1 is 4. So 2 times 4 squared. That's 2 times 16, which makes 32. C0 is still 1. So plus 4 equals negative 6. And let's see. So minus 12 plus 32 makes plus 20. That's then plus 4 makes plus 24. So 6c3 equals negative 30. So c3 is negative 5. So the answers, c0 is 1, c1 is 4, c2 is negative 3, c3 is negative 5. All right. One more. Are you up for it? Okay. Finish it. Finish it. All right. Any questions? Now that I've pulled it away, I can pull it back. All right. So 9 has a similar feel, except classic Steve, we're going to go backwards. So we're given that y, which is the sum, 0 to infinity ckx to k, is a solution to this expression, 1 minus 2x squared y double prime, e to the minus 4xy prime plus xy equals 5 plus 4x. I guarantee you this is worse than what you will see on the exam. I just don't want you to get nervous, but we practice hard ones, so on the exams, they'll seem not so bad. So, we're told that C3 is negative 3 and C4 equals 7. We're asked to find y of 0 and y prime of 0. Can we do this? What's another name for y of 0? C0. And y prime of 0? C1. So what's happened is we are telling you the coefficients a little bit down the road. And you have to work backwards and say, what are the coefficients for the start? Okay, so how do we go about this? Well, the answer is we're going to do the exact same process that we just did. Now let's think about that. We know C0, C1 comes from our initial conditions, usually. So if I was looking for C3, C4, how far would I have to look? Like up to what power would I look? Well, so C0, C1, these would normally correspond with initial conditions. Then the next one would be the coefficient of 1. C3 would be the coefficient of x, and C4 is the coefficient of x squared. Because we have information about C4, where do we want to go? We want to look in this range of 1x, x squared. Other than that, the game's the same. So I'm going to skip a few small things. So let's get right into it. 1 minus 2x squared, polynomial, beautiful, we love polynomials. Mwah! Y double prime. So take the second derivative, 2c0, 6c1x, 12c, I wrote c0, I meant to say 2c2, 6c3. This is what happens when you try to go too quick. 12c4x squared, ... So that's the first part. E to the minus 4x. What can we do with that? We turn into a polynomial. I know this is a series, but think of series as a polynomial. So, maybe we should do that to the side. E to the minus 4x. This is the sum. K equals 0 to infinity. Minus 4x to the k over k factorial. I'm just plugging into the sum. That's on the sheet. So this starts off as 1 when you plug in k equals 0. Anything to the 0, 0 factorial is 1. Minus 4x over 1 factorial. That's not too bad. Negative 4x squared is 16x squared. Divide by 2 makes 8x squared, and ... Okay, so the next term we have, maybe I'll write it underneath here, is 1 minus 4x plus 8x squared plus ... Y prime is c1 plus 2c2x plus 3c3x squared plus ... Plus x times y. Well, y is c0 plus c1x, and we can stop there. Because since we're multiplying the x through, we're already up to x squared. And all of that, when we tally it up, is going to equal 5 plus 4x. All right. Well, let's gather our constants here. So from the first part, our constant term would be 2c2. Our x term would be 6c3. Multiplying the 1 times 6c3x. The x squared term gets interesting. What do we have? Well, we can take 1 times 12c4x squared, and we can take minus 2x squared times 2c2. So that makes it, there's two pieces, 12c4 minus 4c2 x squared. Okay, so that's the first line. Just do it line by line. The second line, our constant term, C1. Our x term. So we're going to go in opposite directions. 2c2 minus 4c1. Yes, 1 times 2c2x minus 4x times c1. So we'll have 2c2 minus 4c1x plus, and again, we're going to move in opposite directions. So 1 times 3c3 minus 4 times 2c2, so minus 8c2, plus 8c1, x squared. And the last line, we should have started here. C0 x, C1 x squared. Beautiful. Okay, so combining, we'll have 2c2 plus c1, that's the constant term. Then we're going to get 6c3, 2c2 minus 4c1, and c0. All right, so plus, nothing combines there. That's okay. Doesn't have to. And then on the end, we have 12c4 minus 4c2, 3c3 minus 8c2 plus 8c1 and c1. So if we plug in what we know, we have 12c4, 3c3, minus 4c2 minus 8c2 makes minus 12c2. 8c1 plus c1 makes 9c1. X squared. All right. Are you surviving? The end is near. Don't worry. We have more paper. Is the process making sense? We're replacing every piece by its part of the polynomial, expanding it out and grouping coefficients. What's true about 2c2 plus c1? It equals 5. That's the constant. How about 6c3 plus 2c2 minus 4c1 plus c0? It equals 4. How about this long piece? It equals 0. All right. Now, I should have done these problems ahead of time. It probably would make me not want to do them again. But, you know, in for a penny, in for a pound, as they say. All right. We do know a couple things. I just want to remind ourselves, we know C3 and we know C4. So C3 is negative 3, C4 is 7. I just want to point out that we can do this. This is, even if nothing else, like, we can actually solve this? Like, yeah, we can. Are we going to do it again? No. But you should always do a problem like this once in your life. You know, otherwise your life just won't have felt complete. All right. So, here we go. 2c2 plus c1 equals 5. Well, Let's just note that that tells us that 2c2 is equal to 5 minus c1. Yes? True? Okay, cool. All right. Now we have 6c3 plus 2c2 minus 4c1 plus c0 is equal to 4. What can we do with this 2c2? It's 5 minus c1, right? And what can we do with this 6c3? It's 6 times negative 3. So negative 18 plus 5 minus c1 minus 4c1 plus c0 is 4. Well, minus 18, you can pull that across as a plus 18. This 5 you can pull across as a minus 5. And so, well, if we do that, so plus 18 minus 5. And what do we have? C1 minus 4, C1 makes minus 5 C1 plus C0. 4 plus 18 is 22 minus 5 is 17. Okay, so that tells us that we now have something about C0 and C1. It's not completely arbitrary. Is it enough to get the answer? No. But we haven't gone all the way. We have more. All right. So, we have 12C4 plus 3. I've got to be careful here so I don't accidentally slip off my page. Minus 12C2 plus 9C1 equals 0. What can we do with the 12C4? We can plug in, because we know what C4 is. 12 times 7 makes 84. Of course it does. 3C3. Wait, what? Plug what in? Oh yeah, we know C3. That's right. Ha! You guys are paying more attention than I am. 3 times 9 is 3. You should take this test. You're going to do great. Okay, now C2, we still can use this, right? So this is minus 6 times 5 minus C1. Because it's minus 6 times 2C2. So this is 2C2. Yes? All right. So what do we have now? We have 84 minus 9, 3 times negative 3, minus 30, then a plus 6, and a plus 9. So plus 15C1. Ooh, good news. That's our favorite kind of equation. One equation, one unknown. 84 subtract 9, 75. 75 subtract 30, 45. Plus 15C1 equals 0. So what does that say about C1? Negative 3. Wow. That was also C3, what? Okay. Okay. Now. Shoop. Negative 5 times negative 3, 15. Plus C0 is 17. So what is C0? 2. So our conclusion is y of 0 is 2. Y prime of 0 is negative 3. So we can solve it. But don't worry, this is not like the one on the test. Thank you for being patient. I am so sorry we had to relocate. Good luck.